So this is lesson 20.4.4, dealing with the period of a pendulum. We started off this unit by talking about two main groupings of simple harmonic motion that we would be studying. One was a mass oscillating on a spring, whether the spring is oscillating vertically or horizontally is not important. The other was a pendulum. And we've looked at a lot of demonstrations with both in one lab with the springs. Today we're going to be solving problems involving the period of a pendulum and also finding the restoring force on a pendulum. When we looked at the restoring force on a spring, on the mass on a spring, restoring force is the force that pulls the mass back to the equilibrium position. And for a horizontal spring, that restoring force is the spring force. It's the force that the spring exerts on the mass. For a vertical spring, the restoring force it's complicated because gravity is at play there as well. So the restoring force is created by considering both the force of gravity and the spring force. For a pendulum, the restoring force is related to the force of gravity but is not the force of gravity, and we'll get to that. So I'm just starting off the same way we started off with springs. I'm giving you the formula that's on your formula sheet for the period of a pendulum. However, there are limitations to this formula. It's 2 pi times the square root of L over G. You'll notice it's very similar to the spring formula. 2 pi root M over K. Just like there are limitations to the spring formula, the main limitation is that you cannot use it for any displacement, because if you take a spring and you stretch it too much, you change the value of the spring constant. The limitation here is this works for small angles. What do we consider a small angle? Well, we're going to do a little demonstration here in a bit, but I would say less than 20 degrees, although you might see in some textbooks the statement less than 10 degrees. And what that means is 20 degrees away from the vertical. And I guess what I'm saying, let me grab the pendulum, but I need my hook. Jackpot. Thank you, Jay. What I'm saying is that we could use this formula to predict the period of a pendulum as long as we don't pull it back more than about 20 degrees from the vertical. And we might as well try this. I want you to get out your phones so that you can do a time measurement. And I am going to use a length of the pendulum from the pivot point to the center of the mass of the pendulum of 1 meter. Now that's not perfect. I'm just eyeballing it. But we're using L equals 1 meter, and I'm just going to get it oscillating. And you can start timing whenever you like. I would like you to time 10 complete periods, which would be the time from the highest point back to the highest point 10 times. I think those of you that were timing it are done. That's at 1 meter. I can always bring it back because we're going to do something else at 1 meter in a second. But at 1 meter, for a length, Zahara, what did you get if you take that divided by 10? 2? So you got exactly 20 seconds?
I had 20.16.
So 2.0,
2.016.
2.01. Brooklyn, did you get a time?
Well, I had 20.14.
All right, you guys are like two peas in a pod.
I also got 20.07, so
2.01,
2.03.
2.03, 2.02, 2.03, 2.01, 2.0 seconds. Let's go 2.01 because we got at least two like that. Okay. What does the formula predict the period will be? Now, I don't know how close this is going to come because I didn't. When I held the meter stick towards the ceiling, it appeared as though the meter stick started at the pivot point because of that hook. But if I use this formula, 2 times pi times the square root of L, which was 1, divided by 9.81. That's what the formula is. That's pretty amazing. That really, I'm not being sarcastic or facetious here. I think that's pretty amazing. I didn't even really take care to ensure that I'm measuring the height perfectly. Now, unfortunately, I've changed the height, so I have to adjust it again. But I want to see what kind of results we get at 1 meter. At 1 meter this time. So this was at, I didn't measure an angle here. This was at about, I think I pulled it back around 10 degrees. And we should get 2.0 seconds. That's what we should get. Let's go with the master timers. Sahara, what did you get?
2.07.
You got 2.0 again?
I got 2.5.
You got 2.5?
1.8.
We're all over the place here. I think we should do that again. I think maybe some people counted wrong, maybe. Did anybody else? Jay, what'd you get? 2.03? 2.03? So it seems to work good at that angle. I don't know, 1 point, I think maybe, did you get 2.5? Have you had coffee today? Well, that's the problem. I'm not happy with that. I'm going to start it again. Are you still getting 2.0?
No, we got 2.1.
What'd you get? 2.1. So the bigger the angle, and that was pretty big. I think that was like 45, maybe 50 degrees off. Here we get 2.1 and 2.1, and we should get 2.0. So the bigger the angle, the further off you are. And you might say to yourself, wow, 0.1 of a second, what's the big deal? The point is it's not giving you the right result. Okay. I pulled this 20 degrees out of the air. I have an idea in my head of why the formula breaks down at larger angles, and that's my estimation of where I think the formula starts to break down. We can look in your textbook a little bit later and see what they have to say about the limitations of the formula. But I would say 20 degrees is a pretty good estimate. Let's run through a few examples, then we're going to do some work with what's called restoring force, and then you're going to have some problems to practice for tomorrow. Determine the period and frequency of a 2.5 meter long pendulum. Now, in this formula for the period of a pendulum, you actually have two variables other than the period. One is L and one is G. But G, for most of our lives, in fact, for probably all of our lives, G is not going to change significantly in our lives. Unless you move to Mexico City, or you go into a cave that's very, very deep under the Earth's crust or in the Earth's crust, G is 9.81 newtons per kilogram. So this is a very basic question. It's going to be 2 pi root 2.5 meters over 9.81 newtons per kilogram. I don't want to get sidetracked into a discussion on units here. Those units, once we take the square root of that combination, is going to give us a period in seconds. So it's just a matter of calculating this. 2 pi root L 2.5 over 9.81, and I get about 3.2 seconds. This was 2.5 meters. I don't know if we have 2.5 meters on this. Let's check it out. I'm going to clearly have to move the table. I don't think it's 2.5. I think it's closer to 2. Well, this is, oh, look at that. I put this together with the inches on the outside. Too bad, it's 2.3 meters. I'm going to change my notes for next time to use 2.3, then we can test it. I'm not going to test it at 2.3 right now. We can maybe do that a little bit later. So it's about 3.1, 3.2 seconds, which is a fairly long time. And if you think about it, I will just get this pendulum going. I will just get this pendulum going. I mean, this should be close to 3 seconds. It's almost 3.5 meters. 1,000, 2, 1,000. Well, it's maybe closer to 2. But it's a fairly significant period. All right, we were also asked to determine the frequency. Well, frequency is the reciprocal of period. This is the period. So we need to take 1 over 3.17 seconds. I never checked. Did you get 3.17 as well? Okay. So about 0.32 hertz. I didn't carry all my decimals, but you'll have to deal with that when you're doing problems. 0.32 hertz. Any questions with either of those? The pendulum has a period of 3 seconds. What's the length of the pendulum? We spent a fair amount of time yesterday talking about the value of algebra as opposed to just putting numbers in. You're trying to use this formula to determine L when you know T. I don't think you should put the 3 in for t to begin with. I think you should simplify it first. This can be simplified to begin with by squaring both sides. And that gives us t squared equals 4 pi squared L over g. This is simpler because it doesn't have a square root. However, it still has a fraction, so I can multiply both sides of this equation by g to eliminate that denominator. And that gives me gt squared equals 4 pi squared L, which means if I divide both sides by 4 pi squared, I get the length of the pendulum. By the way, since the period of the pendulum in the previous question was 3.17 seconds, whatever we get for a length here should be pretty close to the length that we had in the first question. I'm not even going to put the numbers down on the board here. 9.81 times 3 squared divided by 4 and divided by pi squared. Said numerous times in this course, if you don't like the way I go divided by 4 divided by pi squared, then go divided by brackets, 4 pi squared, and brackets. But I get about 2.2 meters. We good with that one? Right? Number 3, a 50 centimeter long pendulum is swinging on the surface of a planet with a particular mass and a particular radius. What is the period of the pendulum? Well, the period of the pendulum is 2 pi root L. L is 0.5 meters, 50 centimeters, over G, but G is not known. It's not on Earth. It's on an imaginary planet. So you're going to need to go to your formula sheet and see if you can find the formula that we use to determine gravitational field strength. And gravitational field strength, we learned this in the unit, I guess it would have been unit 2, dynamics and gravitation, can be found using this little beast of a formula, where m is the mass of the planet, r is the radius of the planet, capital G, of course, is Newton's universal gravitational constant. So G, little g, on the surface of this planet will be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the mass of the planet, which is 2.8 times 10 to the 22 kilograms, divided by the radius of the planet, quantity squared. Let me just step back and make sure I've entered those numbers correctly on my calculator. There's my G, there's my mass of the planet. Did I write those two, the mass and the radius, down correctly, Alex? Okay, good. So the value of the acceleration due to gravity or gravitational field strength where the pendulum is on the surface of this planet is about 10.1 newtons per kilogram. And then we can answer the question, right? Put 10.1 in here. Carry all your decimals, of course, because this could be a numerical response question. And you don't want to get burned by just having the wrong decimal value in your calculation. 2 pi root L, which is 0.5, divided by G, which is my answer. In about 1.4 seconds. So the answer to this question is 1.4 seconds. Any questions with example 3? All right, now we have to talk about the restoring force on a pendulum. And this is different than a spring for a number of reasons. When you have a mass oscillating on a spring, and it doesn't really matter whether it's horizontal or vertical, but I'm going to choose horizontal to make it a little easier to explain. If this is the equilibrium position, and this is the location of the amplitude on one side, and this is the location of the amplitude on the other side, you can say x equals negative a and positive a if you like, but that's not the point. I'm not going to draw a spring on here. I'm simply going to put the box or the mass. And I'm going to ask you to imagine that there's a spring connecting that box or mass to the wall on the left. This thing oscillates back and forth. And I'm not mimicking the speeds that it has. I'm just saying it oscillates back and forth. It's moving as fast as possible here. It stops here, and it stops here, and it does this. Okay? No matter where the mass is, the restoring force is towards the equilibrium position. And that means that any time the mass is on this side, the restoring force is to the right. The spring is pulling it to the right. Anytime it's on this side of the equilibrium position, the restoring force is pulling it to the left. But the bottom line is the restoring force is always a horizontal force. Because this pendulum doesn't move back and forth in a line, it moves back and forth in a curve. I'm going to do my best to show this to you in terms of the directions of the forces on the pendulum. We know that gravity is what's responsible for it moving, right? Gravity is what's responsible for it pulling it from here down to here. But gravity acts downwards. Gravity right now is pulling downward. And the direction that the pendulum is moving at this point in time is this direction. The direction that my pen is pointing. And when the pendulum is here, the direction it's moving is the direction the pen is pointing. And here it's moving in that direction. And here it's moving in this direction. And the restoring force is going to be the force that's... The restoring force is going to be the force that is pulling the pendulum in the direction it's moving. This force that I'm indicating with the pen is the force that's trying to restore the pendulum. And this force is connected to gravity, the gravitational force, but it's also connected to the angle at the top. So going back to our notes and just reading through this, the force that acts to bring a pendulum back to the equilibrium position is called the restoring force. What is the cause of the restoring force? The force of gravity. But the force of gravity is not the restoring force. The restoring force has to be a force that acts in the direction towards the equilibrium position, and gravity doesn't act in that direction. So the example we're going to do here will teach you how to determine the restoring force. So I'm going to add something to this. The force of gravity creates a restoring force. I just really want to highlight for you that the force of gravity is not the restoring force, but it produces the restoring force. So we have one more example we're going to do, and then you have some problems related to this lesson, and you can also work on your lab assignment. What is the magnitude of the restoring force acting on a pendulum with a particular mass if the pendulum is at an angle of 10 degrees? Also determine the linear acceleration at that point in time. So how many meters per second squared is it accelerating at when it's at that 10-degree angle? Well, if we draw this, and I'm going to draw it so that it's more than 10 degrees to make a point. This is the length of string, and that's more than 10 degrees. Okay? Let's draw a bob on there. There's Bob. Pendulum bob, so let's call him Bob. And this angle vertically down from the pivot point is 10 degrees. And again, I know that's more than 10 degrees. That's probably somewhere between around 25 degrees, most likely. But gravity is acting downward on that, and we can draw in that force. The force of gravity acts downward. And this is going to be very similar to what we did when we talked about forces on ramps. This force of gravity does two things. One of the things it does is it pulls the pendulum bob away from the pivot point. So one of the things it does is that. It tightens the string. But the other thing it does is it pulls it in this direction. It's just like a ramp. In fact, let me just clean this up a little bit. In fact, it's exactly like a ramp in terms of motion, because if this was a ball, everybody, and it were on a ramp, and I don't think you want to draw this, but it were on a ramp, and it was rolling down the ramp, then there would be a perpendicular component to the force and a parallel component to the force. Well, the ball is not going to travel in that direction. The bob is going to change direction. But at this point in time, it is moving in the direction indicated by this vector. That's the direction the bob is moving at that point in time. And that's the direction of the force that's acting to move the bob towards the equilibrium position. So this is the restoring force. Again, it's not on a ramp. This was just here to draw a comparison. This must be the restoring force. But that's really easy to figure out, because if, looking at the diagram, if that angle at the top is 10 degrees, then this angle in our vector diagram is 10 degrees. And we know the mass of Bob, so we can calculate the force of gravity acting on Bob. And then it becomes a trigonometry problem, because these two forces, these two components, by definition are perpendicular to each other. So if we can calculate the hypotenuse of that triangle, we can use sine to find the restoring force. And let me write that down to begin with. Sine of the angle will be equal to the restoring force over the force of gravity. And that's going to be true no matter what the angle is. That's going to be true no matter what the mass is. So what we can actually do is come up with a formula that, if you remember it, might save your bacon on an exam, because then you don't have to go through this diagram and this reasoning every time. But let's come back to reality and let's calculate the force due to gravity. It's mg which is, I think it was 0.25 kilograms times 9.81. Which is 2.45 newtons. I think it's probably 2.45005 or something. 4525. Okay. Thank you, Nate. And again, listen, now that you know that, I don't suppose it really matters whether you want to think of a trigonometry problem or whether you want to do some algebra to get to here. The math is up here on the board. If you want to just look at this, then you have a triangle with a hypotenuse of 2.4525, and this is the opposite side, so it becomes a trig problem. If you want to develop this general formula, then you don't need to do that every time. All right, let's see what we get for an answer. I need to multiply that by the sine of 10 degrees, double checking to make sure I'm in degree mode, and my calculator is not, so now it is. The restoring force at that point in time is about 0.43 newtons. Quick question for you. How many of you see that as that angle gets smaller, the length of that highlighted restoring force will become smaller? And how many of you see that as it passes the lowest point, the length of the restoring force will be 0? Because it's at its equilibrium position, just like a spring, except the direction of that force is continually changing. I have a feeling there was something else we were asked to do. Oh yeah, determine the linear acceleration at that point. Well, at this point in time, this is equal to ma. It's the net force acting on the bob at that point in time. The force of gravity pulling it away from the pivot point is canceled by the tension in the rope or string. So if we just divide that by the mass, we'll get the acceleration as 0.43 newtons divided by 0.25 kilograms. I'm getting 1.7 meters per second squared. Yes? Okay. And if you think about this a little bit, you should understand that if we repeat that calculation, and by the way, there's no limitation to the angle. It doesn't have to be less than 10 degrees. If you repeat that calculation, you will discover that the acceleration of the bob here is greater than it is here, and it's greater than what it is here, and at the bottom, the acceleration is 0. Just like a spring. When a spring gets to the equilibrium position, it's not accelerating at that point. A spring accelerates the most at the amplitude, and so does this. All right. Any questions with that final example and set of calculations? All right. Your assignment, there are questions dealing with the period of a pendulum, and there are some questions from your textbook at the end there dealing with the restoring force of a pendulum. If you're practicing on these, you still have about 35 minutes left or about a half hour left. You can also get to work on that lab assignment and see if you can get most of that done.